Now let's talk about substitution with definite integrals. So you can do these problems in the same way that we have done u substitutions before. So do your whole u substitution and then evaluate from 0 to 1 at the end. But there's actually another method that might be easier and is the method that the AP exam would prefer that you do. We're going to start this out the same way. So I see that I have an x squared plus 1 inside of this cube. And so that's probably going to be my u. U is x squared plus 1. Let's take the derivative there. The derivative is 2x dx. I almost have that. I just have an x dx. I'm going to need to divide by 2. Now, since we're changing the integrand to be in terms of u, we also want to change these bounds. The 0 and the 1 are right now in terms of x. We want them to be in terms of u. So what that means is we're going to plug in u of 1 and u of 0. So we're plugging in the bounds into my u so that I can change them so everything's in terms of u instead of in terms of x. So u of 1, I'm plugging it into this u equation, x squared plus 1. 1 squared plus 1 is 2. And u of 0 is 0 squared plus 1, which is 1. So when I rewrite my integral, I'm going to have the integral from 1 to 2. I have my 1/2 from my du balancing. And then I have u to the third du. So notice I replaced everything inside the integrand with u's. I also changed the bounds to be in terms of u. These were x's, now these are u's. I'll integrate like normal, 1/2 times the antiderivative of u to the third is u to the fourth over 4. And I'm going to evaluate from 1 to 2. The nice part about this method, since these are already in terms of u, I can just plug them in for u. I don't need to replace the u with the x squared plus 1. I've essentially already done that by plugging the bounds in. And so what that means is I just have 1/8 times 2 to the fourth minus 1 to the fourth. So I just factored that 4 out in front. 1/2 times 1/4 is 1/8. If I simplify that a little bit, 2 to the fourth is 16. Minus 1 is 15, so this is 15 over 8. So again, if I change the bounds, then I don't need to replace the u at the end. If I didn't change the bounds, if I left those 0 and 1, then I would need to make sure to plug my u back in. Okay, in part B, we have the integral from 1 to 5 of x over square root of 2x squared minus 1. And so again, we'll make our u 2x squared minus 1, just like we would before. Our derivative of that is 4x dx. I'm missing just the 4, so I'm going to divide by 4. Now I also need to evaluate u of 5 and u of 1. U of 5 would be 2 times 5 squared minus 1, that's 49. U of 1 is 2 times 1 squared minus 1, that's 1. So when I rewrite my integral, I have the integral from 1 to 49. That comes from my bounds. I have the 1/4 from the du. And then this was square root of u in the denominator, so we're going to rewrite that as u to the negative 1/2 du. Okay, let's take our antiderivative, 1/4 times u, my new exponent is positive 1/2, so I multiply by the reciprocal, 2 over 1. I'm evaluating from 1 to 49. And so that means I have this coefficient in the front, simplifies to 1/2. U to the 1/2, remember, is square root, so square root of 49 minus square root of 1. You could leave your answer right at this step, but it shouldn't be hard for us to calculate that. That's 1/2 of 7 minus 1, which is 3. Now let's take a look at some AP style problems. In number 4, we have the integral from 1 to e of x squared minus 1 over x. This looks like a u substitution problem. I could make my u x squared minus 1, and then my derivative would be 2x, but then I would notice my dx is in the denominator, and the du would be in the denominator. We never actually want to be dividing by our du. We're always multiplying here. And so what I want you to notice is whenever the degree of the numerator is greater than the degree of the denominator, I will have to divide or simplify before I can take my antiderivative. That's something we will talk more about in 6.8, but we're able to do this problem today. So let's go ahead and rewrite this. X squared minus 1 over x squared over x would just be x minus 1 over x. You can also rewrite that if you want as x squared minus 1 times x to the negative first and then distribute. And now I can just find that antiderivative like normal. I'm going to jump down here. So my antiderivative of x is just x squared over 2. Antiderivative of 1 over x is natural log absolute value of x. And I'm evaluating from 1 to e. So notice I didn't have to do any u substitution because once I rewrote it, I just had single powers of x. So I have e squared over 2 minus natural log of e minus, and then use your parentheses appropriately here, 1 squared over 2 minus natural log of 1. This would be an okay way to leave your answer on a free response, but this is multiple choice, so we're going to have to match up with one of these. So I've got the e squared over 2. Natural log of e is 1. That's an important value to remember. Minus a half. And natural log of 1 is 0. Technically, that would be a plus 0 there. So I have e squared over 2 minus 3 halves. And so my answer is e. In number 5, it seems very similar to what we just did in number 4, but notice that my higher degree term is in the denominator. That's what indicates that this is probably a u sub problem. So I'm going to make my u x squared plus 1. My du is 2x dx. I don't have that 2, so I'm going to divide by 2. And then also, since this is a definite integral, I'm going to go ahead and change my bounds. U of 3 is 3 squared plus 1. That would be 10. U of 2 is 2 squared plus 1. That would be 5. And so then what this integral will become, I have my 1/2 out in front from my du balancing. I have the integral from 5 to 10 because I changed my bounds. And then what I have here is du over u, or 1 over u du. I prefer to write it this way because it makes it more clear how to find the antiderivative. 1/2. The antiderivative of 1 over u is natural log absolute value of u from 5 to 10. So this is 1/2 times natural log of 10 minus natural log of 5. Again, that would be an okay way to leave our answer on a free response. If I check this out up here, though, I don't see any of those answer choices, and so I might have to use my logarithm rules. Remember that if you are subtracting two logarithms with the same base, I can change the argument to be the division of that. So this is going to be 10 over 5. So this is 1/2 natural log of 2, which is one of our answer choices then. If you don't remember those formulas, they are on your Stuff You Must Know cold sheet if you need to review them. So examples like number 6 are exactly why I told you that the AP exam prefers that you change your bounds. They're going to ask you questions that will require you to change your bounds to make a match with a multiple choice question. So for example, in number 6, they give me the u substitution. How kind of them. That's very, very sweet. And so I see that I have the integral from 2 to 4 of 1 minus x over 2 squared. So my u is x over 2. That means my du is 1/2 dx. So I will need to multiply by 2. I need to change my bounds. U of 4 is, x over 2, so 4 over 2 is 2. U of 2 is 2 over 2, which is 1. So I know my integral will be from 1 to 2, so I know it's not going to be b. I can cross that one out. Then I have my integral from 1 to 2. I have my 2 out in front. I had to multiply by 2 there. And then I have 1 minus u squared in the numerator. But notice I have this extra x down here, and that comes, this is that change of variable problem at the same time. If u is x over 2, that means that 2u is equal to x. So I can replace the x with the 2u at the bottom, du. Now this isn't any of my answer choices, so I'm looking to see, can I simplify it all? I see I can cancel out that 2. So then I have the integral from 1 to 2 of 1 minus u squared over u du, which is d. Make sure you're checking your answer choices here. You don't actually have to find that integral. I'm just matching the setup. Also be careful. C would be if you forgot to balance your du's here. A would be if you multiply by 1/2 instead of multiplying by 2 when you rewrite that. So just watch out for those problems. And finally, example number 7 is a way they can do these problems with tables. So it tells me f and g are differentiable. That's nice to know. F and g are given. We want to evaluate this crazy looking integral, the integral from 0 to 5, g prime of f of x times f prime of x. What hopefully you notice is that this looks kind of like chain rule, a little bit off. And so when a problem looks like I would use chain rule for derivatives, when I do antiderivatives, it's going to be a u substitution. So my u will be my inside part. U is f of x. I recognize that that's inside the g prime function. The derivative of that is f prime of x dx. That's nice, that's there. And then I also need to find u of 5 and u of 0. So I'm plugging in my bounds here. U of 5 means I'm doing f of 5, which is 3. And u of 0 means f of 0, which is 1. And so when I rewrite my integral, I have the integral from 1 to 3 of g prime of u du. So now everything's in terms of u's. I don't have the f's anymore. I already dealt with those. So I can just now take the antiderivative of g prime. The antiderivative of g prime is just g, still g of u, evaluated from 1 to 3. So that gives me g of 3 minus g of 1, which is 3. So g of 3 I can see is 3, minus g of 1 is 10. So my answer here is -7.